Okay, got it. Yeah. Some work I did a few years ago with Paul Balister, who's in Oxford. He was in Memphis at the time, now he moved to Oxford. Béla Bollobás, who has been in Cambridge for a very long time. He was also my PhD advisor in Memphis, and also as a visiting professor at IMPA every year. Julian Sahasrabudhe, who was a postdoc at IMPA and now is a lecturer in Cambridge, assistant professor. And Marius Tiba, who was also a postdoc at IMPA and now is a postdoc in Oxford. Okay, so I'm not going to assume you know anything about any of this, but so please do tell me if I'm going too slowly or too fast or whatever. So yeah, please, as many questions as possible, because I'm used to an audience with a different background, so I might not know exactly what speed to go. So try and get this to work. So okay, so what is a little polynomial? So it's just a polynomial degree n, where all the coefficients are either -1 or 1. Okay, so no zero coefficients. You really have n plus 1 coefficients, and they're all -1 or 1. Okay, these were studied a lot from sort of almost 100 years ago by people like Littlewood and Offord and Polya and Erdös and various people. In particular, Erdös asked this question, purely motivated by a lot of this work by Littlewood and others. He said, all right, if you take a Littlewood polynomial and look at the image of the unit circle in the complex plane, so it kind of goes like winding round like crazy. Can you make it so on average? It's not difficult to show that on average the distance is about √n from the origin. Can you show that? Can you find a polynomial such that it's always roughly distance √n from the origin? This inspired Littlewood to work on this and related questions a lot in over the following 10 years, so the later part of his life. And 9 years later, having thought about this quite a bit, he conjectured that it was really true. And he also included this in his collection of 30 problems, published in 1968, and spent quite a bit of time talking about this problem and various failed attempts that he had made to solve it. Okay, so what's going on with this question? Well, okay, the first thing, at least someone like me might think of, is, all right, what happens if you just take a random polynomial? Maybe a random polynomial works. Okay, here's a picture of a random polynomial. So all of the pictures in this talk are taken from a very nice and helpful survey written by Lidsko a few years ago. We found this quite useful when we were thinking about the problem, and he has lots of nice pictures of simulations. So here's just a sort of well, not really a random polynomial, but sort of a quasi-random polynomial of degree 127. And as you can sort of see, it kind of looks like a Gaussian, right? So what's happening with a random polynomial? You're adding up a bunch of basically random plus or minus ones. So you might expect that your position looks something like a Gaussian. Right, so the density is higher in the middle and kind of it tails off towards the sides, except there's obviously some correlation between the different points, right? That if two values of z are close together on the unit circle, they're going to get a value that's close together, that the image is going to be close together. You get these lines, so there's this sort of correlation that you have to worry about. But roughly speaking, we should think of this as being a bit like a Gaussian. Okay, and there's a perspective that I'm gonna try and take throughout the talk. Okay. Well, okay, so you see that, okay, if it is a Gaussian and the average distance is √n, then you might expect Gaussian tails. So you might expect the polynomial doesn't get much further than, say, like √n log n or something. And this is really true and can be proved without too much difficulty. So the upper bound is not sort of super far away from the truth, right? It's only a factor of log away from what you want. But for the lower bound, you're in big trouble. So you want to try and keep everything far away from the origin, but in fact, it's super clustered around the origin. And in fact, you get as close as, I think, 1/n² or something crazy to the origin. You really get very close. Okay, so this is very good for the upper bound, or pretty good for the upper bound, but absolutely terrible for the lower bound. Okay. However, it had already been shown that, so you might think the upper bound is perhaps the first thing to try. And in fact, it had already been shown by Shapiro in his master's thesis, and then rediscovered by Rudin a few years later, at the time when Erdös asked this question, that you can get the upper bound. So you can really get rid of this log factor that you get in a random polynomial. You can get to the optimal thing up to a constant factor, but then it becomes 5. And the construction is very simple. So these Rudin-Shapiro polynomials, which you may well be familiar with, where you have these two sets of polynomials, and to select the next one, so the length 2 to the t, you take the previous one, the q, and then the p, and then you take the q either next to it as it is, or next to it and switched. Okay, yeah, that's sort of this very simple and elegant construction, and it's not difficult to show. It's just a simple induction will allow you to show that you get its upper bound. Okay, so the upper bound actually is relatively simple. Okay. Sorry, and yeah, these are Littlewood polynomials. Okay, so the upper bound. So why do we even think the lower bound should be true? Okay, the upper bound wasn't even a random polynomial got close. Okay, maybe it's natural to think you can get rid of this log factor. But the lower bound, we have nothing close at the moment. So why should it be true? Sorry. So let me show a picture of this Rudin-Shapiro polynomial. So yeah, beautifully tucks in from the outside, but terrible in the middle. Okay. Sorry. So before coming to that, so far there's no probability. There's not really very much combinatorics. So why is someone like me even thinking about this? Well, we were inspired by this development. We started with Beck in about 40 years ago, who introduced a new probabilistic ideas into discrepancy theory, and Spencer sort of used this method, discovered that you could use it to solve a bunch of well-known problems. So perhaps most famously, he proved this 6 standard deviations device theorem, that says for any set of subsets of 1 up to n, of n subsets, you can red-blue color the vertices so that the colors are almost balanced on every set. Okay, this was a well-known question of Erdös. And in the same paper, using very similar techniques, he gave another proof of this upper bound, except he didn't just find one polynomial or a small family, he found exponentially many. Okay, so there are actually a huge number of Littlewood polynomials of degree n that satisfy this upper bound. And so I next want to sort of try and explain why this is sort of a natural thing that you would expect.
Sorry,
okay, so
please.
Sorry, the discrepancy means so on each edge, on each set AI, the discrepancy is the difference between number of red and number of blue points.
Oh, okay.
And the discrepancy of the hypergraph is the maximum of these things. So all sets have all sets have discrepancy basically as small as you could hope. Yeah, so it knows that this Littlewood polynomial problem is actually closely related to this more combinatorial questions, these combinatorial questions in discrepancy theory. Okay, so why should this be true? So why should there be many of these things? Okay, so let's try and give a heuristic which explains what's going on. Okay, so let's look at the polynomial at 2 different values, z1 and z2, on the circle, and what the probability that each of them individually, if you think of the things as being random, like of them being distant large constant times root 10 from the origin. Well, if it looks like a Gaussian, if our polynomial is random, like, then if it's random, then the probability will be e to the minus c squared, so like in a Gaussian. The problem is that if z1 and z2 are close together, then these things are highly correlated. Okay, and the distance at which the correlation really kicks in is roughly 1 over n. Okay, but if the distance between them is a lot larger than 1 over n, then they're roughly independent. So this sort of scale 1 over n is roughly the distance apart at which they're becoming very correlated to pretty independent. Okay, so suppose we believe these three claims. Well, okay, now if we look at the mth roots of unity, let's think m is maybe some large constant times n or something. Then what's the probability that all of these roots of unity are less than constant root n. Each one individually is like 1 minus e to the minus c squared. Okay, they're not quite independent because they're still at distance 1 over n, but let's just pretend they're independent. So then we get to just multiply all probabilities together. And this is much bigger than 2 to the minus n, right? As long as c is, is large. Okay. So, right. So I'm sort of, this is definitely cheating because, I mean, right, I want this m to be actually a lot smaller than n in order for them to be independent. But I guess I'm claiming that between these roots of unity, if you're good on the roots of unity, maybe you're good in between them as well. But then they should be much closer than 1 over n to do that. So there's this scale 1 over n that I'm kind of brushing under the rug. But roughly speaking, okay, if you give me that, then right, the expected number of polynomials that are good on these roots of unity is large, and maybe in between them we can do something controlling the derivatives maybe to stop them doing something too crazy between these roots of unity. Okay, this is a very rough heuristic, but I guess the point is that we're winning by, like in this, if you can see highlighted, we're winning by a lot here, right? We're really winning by a huge amount. You see that there's sort of exponential factors fighting against each other. And if C is large, actually, this is sort of a big exponential factor fighting with a tiny one. So we have some hope. And this isn't how Spencer proved it, or not, perhaps not exactly, but this sort of motivates why one would hope it was true. Yeah, but it's not fair to say that it wasn't. I mean, this is perhaps the sketch version of how we proved it. Okay. Okay, so here's a heuristic, and it turns out actually there's a theorem corresponding to it. So maybe we can believe the heuristic. Okay, let's try and apply the same heuristic to the lower bound. See what happens. Okay, so the same heuristic. We're going to look at these pairs of points. And now, okay, again using this Gaussian intuition, each is within a sphere of radius, a disk of radius delta root n, with probability about delta squared. Yeah, that's how much of the volume is there. Right, just the area of the disk compared to the root n disk. And again, they're highly correlated if they're closer than 1 over n, and basically independent if they're much bigger than 1 over n. And then there's this region between where we're not quite sure. Okay, so let's use the same kind of argument. So again, let's take the mth roots of unity. So we think of m as being sort of large enough that we can hopefully control what happens in between. Then right, the probability that on all of these roots of unity are bigger than delta root n is about 1 minus delta squared to the m, assuming independence, which we know isn't true, but maybe it's sort of almost true. And that's again much bigger than 2 to the minus n. 2 to the n Littlewood polynomials, so the expected number of good polynomials is large. So if this heuristic is true, these things should exist. Okay, they should be sort of random-like, but if you take a random one, it's not typically good. But so they're going to occur with exponentially small probability, but maybe the exponent in the exponential is not so terrible that they don't exist at all. Okay, so we're searching for this object which is exponentially unlikely, but still sort of likely enough that it should exist. Okay, any questions at this point? Okay, so right, we want to find this sort of exponentially unlikely object. Okay, and this is sort of what discrepancy theory is kind of all about. Okay, another more reasons to think it might be true. There do exist these things with relatively low degree. So here's the Barker polynomial. That one's pretty good. But let's go did an exhaustive search up to degree 50. We found this is the best one of degree 50. Okay, it seems like it's pretty staying away from the origin, and also a sort of not completely exhaustive search, but a sort of semi-exhaustive, and found this one of degree 92. And it's sort of interesting to see that the ratio of the inner circle and the outer circle don't seem to be changing very much from 50 to 92. Right? This sort of fits in with the heuristic. You wouldn't expect from the heuristic to be able to make this disk sort of it shouldn't be getting thinner and thinner as the degree goes up. It should be staying at roughly the same or should be approaching and some asymptotic shape, this annulus. So the simulations seem to be really supporting this heuristic idea, right? Because if instead of this delta squared you put sort of 1 minus delta, then the exponential you'd be getting down here would not beat 2 to the n. Right? It would be a worse exponential. There should be, according to this heuristic, a critical value of delta, which maybe should be about a half or something, at which this 1 minus delta squared to the m starts beating the 2 to the minus n. Okay, and it's not clear exactly what it is because m isn't exactly n, so there's some sort of, we can't make a clear prediction of what the constant should be, but just roughly speaking, this is fitting in with what we might expect from this probabilistic intuition. Okay, so this is sort of a useful picture, a useful sign that we're not doing something too silly. Okay, so what lower bounds are actually known? Well, a long time ago, Carol, Eustace, and Figuel gave a simple recursive construction. They gave this polynomial bound, so something not too bad, but still quite a long way from root n. Famously, Kahan proved a few years after this that if you relax things, so your coefficients are no longer plus minus 1, but they're anywhere on the unit circle, then you can actually do much better. You can really get this so-called ultra flat polynomials, where the distance from root n is a lower order term. But this also fits in with our intuition, because now instead of having 2 to the n choices, we have way more choices, right? Even if you just allow the nth roots of unity, you have n to the n choices, and the heuristic would predict in that case that you can find these ultra flat polynomials. Okay, so there's actually more evidence in favor, and even more, Beck showed 10 years later that you can really do this with kth roots of unity, and you don't even need n roots of unity, like something like 400 will do. And as the number of roots of unity increases, then your error tends to 0. So everything exactly as the heuristic would suggest. Okay. So the main theorem is that this is really true. So the random intuition is correct. There really do exist these polynomials, right. So we get some explicit constants. So the constants are put in just really to emphasize that the lower bound is much harder than the upper bound. So the upper bound, we can get a 2 to the 12 without really trying too hard. I mean, we didn't try to optimize this at all, but really sort of we're kind of forced to have a very small constant here. Like our proof will not work with 2 to the minus 10 or something. We really need some fairly small. Okay, so for the rest of the talk, I'd like to try and give you some idea of the proof. The proof is surprisingly simple. It's a fairly combinatorial argument, but using some basic things from number theory. So I know I assume you'll find those are very simple, but we'll go through and see. Okay, so what's the basic idea? Here's a rough idea up to polylog factors. So I'll tell you at the end how to get rid of the polylog factors. But if you don't mind losing a factor of log in the upper bound and the lower bound, then it makes life a bit simpler. Okay, so the basic idea is to use the 2 dimensions of the complex plane independently. You're going to do different things with the real axis and with the imaginary axis. And for us, it doesn't actually matter which one we use for which, but okay, so we really want to use them for different jobs. So in one of the dimensions, we're just going to choose a random polynomial. So in the real axis, say, we're going to have a thing that's just zipping back and forth like crazy, just doing something random. And okay, so when the real part is big, like large and positive or large and negative, we're already happy. It doesn't matter what the imaginary part is, we're far from the origin. I'm just trying to prove the lower bound now. What we have to worry about is when the real part is close to 0, which of course it will be. So we're going to use the imaginary part to push super hard whenever the real part is close to 0. Okay, so I'll explain exactly what we mean by pushing, but we get some choice, right? And we can decide, we can choose the coefficient in order to try to sort of force the polynomial away from 0. Okay. Okay, and we get to do the pushing when you use ideas from discrepancy theory. Okay, this is the basic outline of the thing. Okay. Okay, so what do we mean by this? Okay, so first, how are we going to use the two dimensions independently? So my next slide is the one where if I talk to people from combinatorics, they get very scared. But presumably for you guys, this is going to be very simple. So just let me know if so I'm going to try to find a balance between. I'll go through this very slowly with people from combinatorics. Because I mean I'm the same way. I'm not really familiar with these things. Anyway, so we're going to choose a partition, which is going to correspond to the cosine and the sine polynomial. You'll see in a second. So right, so we're going to define these epsilons to be either equal or opposite, and define this polynomial. So right, this is no longer a polynomial, right? The coefficients go from -2n to 2n instead of from 0 to n. But of course, you can just multiply by z to the 2n to get a polynomial, an actual polynomial of degree 4n, and it's going to have the same property. You're just rotating. Okay, so doesn't do terrible. The advantage of this is that now we can decompose this thing by our choices up here as a cosine polynomial, a real cosine polynomial, and an imaginary sine polynomial. Okay. Okay, so I guess for you guys, this is not as scary as it is for people from my area. Okay, so what do we want? We want to choose sine and cosine polynomials so that both of them are not too large, which is going to be the easy part, and then the difficult part, so that whenever the cosine polynomial is going to be random-like, it's going to zip back and forward. Whenever it passes 0, we're going to make sure at that moment the sine polynomial is large, either large positive or large negative. Okay, it's a pretty simple strategy. Okay. Okay, so how are we going to do that? So we want this guy to be large everywhere. Okay, so let's suppose we've already got our cosine polynomial, which you should think of as being random, and consider the times when it's close to 0. More precisely, when it's smaller than delta root n. So these are the danger zones. Okay, so the thing's zipping back and forward. Whenever it goes close to 0, we say, okay, we're going to mark that interval on the circle and say that's a dangerous interval. Okay, let's suppose there's m of them, and I guess m is going to be at most like 4n or something, just by whatever that's the number of roots they have. Okay. Right. So we want to choose these coefficients of the sine polynomial so that on each of them the sine polynomial is large. Okay, on each of the dangerous intervals. So how are we going to do that? So right. So what does each choice do? On each interval, it pushes you vertically either up by sine of k theta or down by sine of k theta. Right. Now, okay, so I'm treating the sine k theta as if it's a single theta, actually it's an interval, right? If the intervals are short, then maybe we can think of it as just being a single number. And if they're well separated, far apart, then maybe we can think of them as being independent. So maybe it's reasonable when trying to figure out how to do this to think about each of these numbers, sine k theta, this vertical push, as being an independent random element of -1, 1. Okay, just as a kind of a toy version. If we can solve that, maybe we can solve the original. So this leads us to right. Sorry, and yes, I also want to think of them as being random, even though they're not random. But you know, we chose the cosine polynomial to be basically random, so maybe it's a reasonable way to think about it. Okay. So this takes us to a toy problem. So this toy problem is really sort of at the heart of what we're doing. So in the toy problem, we have m balls, and they're on the integers, and they start all at 0. And each of these each ball corresponds to a dangerous interval. Okay, an interval on the unit circle where the cosine polynomial is near zero, or we want to push very hard, either up or down, which in this picture corresponds to either left or right. We're going to push these balls away from zero. And what does pushing mean? Well, in each step, we're going to choose an epsilon k to be plus or minus 1. So we're given a random subset of them, which correspond to the ones for which sine k theta is positive, right? We're thinking of these sine k thetas as being random plus or minus 1s. So half of them are going to be plus and half minus. Okay, so I'm going to color the plus ones as black and the minus ones as white. Okay. And then when I choose epsilon k to be plus or minus 1, what I'm saying is either I move the black balls to one to the right and the white balls one to the left, or vice versa. Okay, so choosing epsilon k means you decide which way the black balls go and the white balls go in the opposite direction. Okay, so that's a single value of k. But we get to do this n times. We're going to do this for every single k. I'm going to imagine that, okay, all right, and the other balls move the opposite direction. And then for the next k, we get a new random subset of the balls. Okay, it's not really random, it's exactly the ones for which sine of k2 theta is positive. But let's think of them being random. We get to choose if we go left or right. Okay, this time they went right. And so on. And we repeat this for n steps. Okay. And our task is to push all the balls away from the origin, away from zero. We don't mind if they go left, if they go right. We don't want any of the balls near the middle. So the question is, can we do it? So when we were thinking about this, we came up with a bunch of very complicated strategies, which none of which seem to work in a simulation. But it turned out all the complicated part wasn't really necessary, because the strategy that essentially works is extremely simple, or works essentially as well as any of the complicated ones. So here's the very simple strategy that will essentially work for pushing balls. So for each ball, we're just going to choose from the beginning, before we see any of the randomness, if we want to go left, if we want to go right. Okay, any way you like, maybe randomly. It's just going to stick to that direction. It's going to try and move in that direction. So at each step, how do you choose whether epsilon k is plus or minus 1? Well, each ball wants to go, suppose the ball wants to go left, then it says, okay, I vote to go left. I vote for me to go left. When you add up the votes, right, it gets randomized whether that counts for epsilon k being plus or minus. It's like you have two political parties. People on the left are voting for the left. People on the right vote for the left. Actually, when you count the votes, you randomize them first and then add them up. Okay, but because each vote actually is for that person going left, we choose the direction with the most votes, right? And that's the one we go. So why should this work? The fact that you are voting, so the votes are randomized. So if you have m balls corresponding to m intervals, then the winner is going to the winning sort of direction is going to win by an average about root m, right? So what's the probability that your vote is pivotal? Your vote is pivotal with probability roughly. So how far do we expect to have pushed a ball? Just depends on how important your vote is, right? Everyone else is voting randomly as far as you're concerned. So what's the drift of your ball? It just depends on the probability that your vote is pivotal. And your vote is pivotal with probability about 1 over root m. Right? So your influence, as people call it, is roughly 1 over root m. So the probability that your vote decides the election. Okay. And so your steps will be random every time your vote doesn't matter. Every time your vote matters, then you'll go in that direction. Okay. Alternatively, you can just think the probability that you win is a half plus 1 over root m, because you're voting in that direction. Okay, so after n steps, your drift, if your drift is sort of 1 over root m in each step, you'll typically have moved distance n over root m plus or minus. So the random votes give you plus or minus root n. That's how far you'll have moved, more or less. So do you expect to have moved in your direction? Well, not at the beginning. At the beginning, it's just random. But after long enough, the drift will overcome this randomness. After roughly m steps, you can expect to have moved in your direction. Okay, you can expect to move in direction. I mean, to get everyone to have moved in their direction, you need a bit more than m, right? Maybe m log m or something. But at least you can, you don't really have a hope of this working until m steps. Okay, but from roughly m steps onwards, then you have some hope. You start sort of seeing macroscopically that the balls are drifting in their preferred direction. Okay, it's the scale at which it's happening. So we'd like n to be bigger than m, preferably a lot bigger. But now we have a problem. That what did we say m was? M is the number of dangerous intervals. What's our bound on the number of dangerous intervals? We have a cosine polynomial. It's the roots, or it's basically the number of roots. So it's like n or 4n. So actually m is bigger than n. So it can't work. And this is why none of our complicated strategies worked either. There was always just it's just not quite enough steps. So what can we do? Well, actually, we do something. The solution is incredibly simple again. We don't want to have n roots. We want to have small constant times n. We want to have little n, little o of n roots. All we do is we choose our cosine polynomial to have lower degree. Okay, so we don't take a cosine polynomial of degree n and a sine polynomial of degree n, we get a cosine polynomial of degree gamma n. And then automatically it has only 4 gamma n or 2 gamma n roots or whatever. So there's only 4 gamma n intervals which are dangerous. And now, if you don't mind losing polylogs, we can literally just choose the cosine polynomial randomly. Choose gamma to be like 1 over log n squared, and then what happens at least in this heuristic, is that the push is now much bigger than not just root n, the typical deviation, but root of n log n, which is like the maximum that you're going to get. So the maximum over these n balls of the deviation by randomness is going to be in the wrong direction. It's going to be root n log n. And if your n over root gamma n is bigger than that, then you're going to win. Okay. So if you don't care about polylogs, this is basically the proof. Okay. Okay. You have to figure out how to make it rigorous, but yeah, it's not sort of not super difficult. Okay, so I'm going to try and explain how to get rid of the log factors. Okay. So are there any questions at this point before I talk about getting rid of the log factors? No? Okay. Okay, so how do we get rid of the log factors? Well, instead of using a random polynomial, we need some. So for the upper bound, the random polynomial is going to give us an error on the upper bound with a log. So then we can use the Rudin-Shapiro polynomials. So not exactly, they don't work just as they are, but we'll use a modification. For the lower bound, there's a problem with the strategy is that I was doing it online. So we're saying, okay, let's come up with a strategy which says, okay, you're given what's happened so far. You want to choose the next direction. So that means you're doing it online. You have to, at each step you have to make a decision. Doing things online is more difficult than doing it offline. If you could see all of the random sets from the beginning, then maybe you can make a cleverer decision. You can use all the information from the whole world, not just from what you've seen so far. So we'll replace an online strategy with an offline strategy, basically based on Beck's ideas and Spencer's theorem, so the things I mentioned before. Okay. So first, what do we do with the Rudin-Shapiro polynomials? Well, if we just take the Rudin-Shapiro polynomials as they have this nice upper bound property, and we randomize them by multiplying them by these z to the t and z to the 2t, where these are chosen so that the degrees are correct. Well, these very quickly oscillating terms, z to the t and z to the 2t. So why do we want the polynomial to be random? Well, we said earlier that the properties we need of these intervals are that they're short and well separated. So we don't want the cosine polynomial to wander into zero and hang out there for a long time, and we don't want it to leave and then come back straight away. And by taking these, by using these terms that oscillate very quickly, we can prevent that from happening. Okay, we just make sure that the thing is whizzing backwards and forwards at a high enough speed that nothing goes wrong. It's not very difficult to prove this. It's just it's a very simple sort of exercise, just a couple of pages of very simple analysis. Okay. Okay. Right. So for this cosine polynomial, because it has these two properties, the dangerous intervals are short and well separated, then our other heuristic should hopefully work. Okay. So how do we do the pushing? So instead of doing this very simple strategy I said, which loses this log factor, we're going to use a variant of Spencer's theorem. So this variant was proved by Lovitz and Mecca a few years ago, and so their actual motivation for doing this was it gave an algorithm for finding a solution in Spencer's theorem. Okay, so the statement is a little bit. Tiny bit complicated, but it's really quite simple. So right, so we're working in this continuous box -1 to the n. We have a start point x0, and we have various vectors that correspond to hyperplanes. Okay, so v1 to vm are going to correspond to m hyperplanes. Okay, they're cutting through this box. We start x0, which is somewhere on one side of the inside of all these hyperplanes, and we have some constants. So don't worry, they're going to satisfy some condition. Basically, think of the c's as being constants. But if m is large, you can allow them. They got some decaying property, so you can allow m to be much bigger than n if you want, as long as the constants are growing suitably. Okay, and what does it tell you? It tells you can find a vertex of the hypercube such that in each of these directions, these VKs, right? So each one corresponds to sort of a hyperplane. So these inequalities all correspond to, did you hit a certain hyperplane? Right? Did you go constant root n in the direction VK? They're saying you don't have to. That as long as these constants are sort of large enough, then these hyperplanes don't eat all of the vertices of the hypercube. Okay. And the way they prove this is beautiful. They basically just run a Brownian motion, and if it hits one of these hyperplanes, it sticks to it. You do the Brownian motion inside the hyperplane. Hit another one, you stick to that as well. You do a Brownian motion in the lower dimensional space. If you hit a side of the hypercube, you stick to that as well. You just keep running this until the dimensions sort of gone down by a factor of 2 or something. And they say, okay, now we stop. And then we iterate with a different error. Okay, so the CKs, you don't have the same, but you say, okay, let's loosen everything a bit and run it again. And each of these steps, you fix at least a constant proportion of the vertices, of the directions, and some not too difficult analysis tells you it works. It's a really wonderful proof. Okay, so why is this useful? Well, because, okay, now we don't have, in reality, we don't have random directions, right? We have, we don't have random sets that we're getting. We're getting these sine k thetas. We need to really deal with the sine k thetas. But we can just apply this theorem with the vectors, so these vectors defined these hyperplanes, being essentially, I mean, this I sub I is the ith dangerous interval. So we're just looking at essentially the value of sine k theta on that interval. The intervals are short, so this integral is really just the value. So, okay, so that's how hard we're pushing in each direction. Okay, and that corresponds to the VK in the theorem. Aha, and we also so we want to control these derivatives of the polynomials as well, because we're only controlling it on the interval, and we don't know. We want to say, okay, at certain points that you're good. You don't want to say, okay, nearby it doesn't do something too crazy. We just control all of the derivatives, then it's no problem. We can just then use Taylor or whatever to make sure everything's fine. And notice, so we can do this for this enormous collection of vectors, because in Lovett-Mecker's theorem, there's no bound on m. We can do m as large as we like, as long as we allow the errors to increase. So we allow the errors on the derivative to be bigger than the errors on the original, on the second derivative to be bigger again, on the third derivative bigger again. And because in Taylor you have this 1 over k factorial or whatever, everything's fine, everything converges. There's no problem. Okay, so we use this theorem to control not only the values of the sine polynomial we're pushing, but also all the derivatives. So the basic idea is that you want to push super hard, either plus in the direction of either plus or minus, so your expected value is very far away. You're basically using this theorem to make sure you're close to where you want to be. So this sort of this x0 corresponds to sort of where you want to be. So I mean, more technically, you sort of you take a Fourier transform and you pick your x0 to sort of, you're approximating the sort of step function that you want to get. I mean, each guy you go, I want to get up, I want to go down, and you're approximating the step function with some sine polynomial. Right. Okay, so that basically proves the theorem. Okay. So it's really, so even, I don't know if the last part seemed a tiny bit technical, but the details are actually very simple. There's nothing very difficult happens at any point. Once you have the strategy, then carrying it out is it's technically very straightforward. Okay, so we get the,
can you explain what's the DJL in the last slide?
Sorry, yes. So your theta is this is the root of unity. So the J is the root of unity that you're controlling, and the L is the derivative. So for each derivative, we want to control all of the n roots of unity. And I guess we just can control all of them. There's no problem with it. So it's only so for the original guys, we really want to only control the m intervals. We want m to be much smaller than n. But once you're controlling the derivatives and things, you can sort of give away some large constant factor, and so life becomes simpler.
And the C case here will be what?
So these will be so sorry. You can also renormalize everything. Sorry. If the technical version doesn't have this condition that the v's are small, but you can multiply everything by the infinity norm of the v's. Yeah, so we just renormalize. So whatever happens to be, just renormalize it.
Okay, so the C case are like the infinity norm.
So the CKs are just what we're multiplying everything by, but I should also really multiply also by the infinity norm of the VI.
Nice.
Yeah, so I wanted to make the statement a little bit cleaner, so I removed that. But yeah, you're right.
Okay. Thanks.
And how far up in L do you have to go? Like all L, or
We can just do all L. So yeah.
okay.
More questions? Okay, so sorry, just to recap. So the idea was to choose a cosine polynomial based on the Rudin-Shapiro polynomial, just adding this highly oscillatory term, which is then automatically at most sort of constant root n everywhere, and the places where it's small are few because it's low degree, short and well separated because it's oscillating very fast. Now in each interval, we need to choose a direction to push in. And then using these results from discrepancy theory, we can make sure we really do. So you sort of expect to push this far, and you make sure that you only sort of you push that far plus or minus some error. And the error is big O root n essentially by Spencer, by Beck. Okay. So technically by Lovato-Mecca, but okay. Right, and this gives us a sine polynomial that's the most in the end 2 to the 10 times root n everywhere, and pretty big on each of the dangerous intervals. So the dangerous intervals actually we push really hard. We can go sort of way bigger than delta root n. Okay, so the thing we get in the end actually looks sort of some crazy thing that sort of every time it's close to zero in the real direction, it's huge in the imaginary direction. Yeah. But unfortunately, this is small constant. Okay, so there are still lots of open problems. So perhaps the most famous of these is Erdös's question from the same set of problems. So this comes from a collection, a paper he did, which was just a collection of problems. He asked whether there exists ultra-flat Littlewood polynomials, whether you can get this 1 plus little O1, so this constant factor, maybe, is it really necessary? I think he asked this in the other way around. I think he perhaps expected already that they didn't exist. So Kahan proved that they do exist if you allow complex coefficients, but again, that's to be expected. But numerical evidence, so from Alisco's paper suggests these pictures we showed at the beginning, at least going up to degree 100, suggest they maybe don't exist, which is also what the probabilistic, the heuristic suggests. So I think it would be surprising if they existed. I mean, that doesn't stop them from existing for some crazy algebraic reason, but right, I wouldn't expect. So I think what this suggests is that to answer this question, the probabilistic approach is not the right thing to do. This is more of an analytic or an algebraic question, and so I suspect it's more for you guys than for me. But I think it's a wonderful question, and probably the answer will be, I mean, either some magical algebraic construction, or probably more likely some very clever argument to show that such a thing cannot exist.
So in your result, do you have any conjecture for the constant, like the best possible constant in the upper and lower bound?
So we don't have one, and it's not really clear that the heuristic will give you something that precise because of this confusion about the correlation at distance 1 over n. So it's not really clear what the correct number of roots of unity to look at is. It's some constant times n.
Yeah, for the Rudin-Shapiro, I think the best one isn't like root n or something. It is none.
So Rudin-Shapiro, so my co-author Paul Balister proved the correct constant for that.
Yeah, it's root n or something.
So it's some particular constant, root 3 times root n, or something with a
Yeah, so I was wondering,
root 3 minus 1 or something weird.
Yeah.
Right. So I don't think that's my guess would be that it's not the real optimum, but right, I don't have a strong reason to believe it. Just why should something so simple be the best? If it is, that would be wonderful. For the lower bound, then I would guess that the optimal thing looks fairly random like. I mean, from the simulations, it looks like it's something like, I don't know, root n over 2 or something, or 2 root n over 3. I don't know. It's probably some weird number. I don't see any way to come up with a. We did think about it a bit. I don't see any way to come up with a really natural conjecture, just because the correlation is so important and it tails off so slowly that the rate at which the correlation between the adjacent roots of unity tails off will affect what you'd expect, even from the heuristic. Yeah. So I mean, it's another very natural question and probably a very difficult one. But again, given that we can't even show that ultra flat ones don't exist, then it seems somewhat hopeless at the moment. Yeah, I mean, I think this is the next. The next big challenge will be to answer this question, probably in the negative. Right. So some other sort of just related questions. I mean, I guess I put these slides in more for the combinatorial people, but I'll show them to you as well. So there's beautiful result of Beck and Fiala about discrepancy in hypergraphs with maximum degree D. So it's the same problem as I mentioned before, but now the set of edges, the sets, each vertex should only be at most D sets. They proved that such a hypergraph has discrepancy less than most 2D, and conjecture it should be really root D. And very little is known. So Boris Book managed to improve this 2D by a additive log star. But yeah, really sort of very little is known. So I guess I should say that there is our results of the form sort of root D log n or something. So if you allow some log factor of n, then you can get it. There's been a lot of really nice recent work on random and random hypergraphs. So this is a list from when I wrote these slides a couple of years ago, but even since then there's been a bunch more work. And then just finally, there's this more general conjecture of Komlosh. So this is a really beautiful conjecture and perhaps easy to understand if you're less familiar with discrepancy. So we're just going to take any n vectors in R to the n, so unit vectors or size at most 1. Can you find a collection of plus or minus 1s such that adding up these vectors or minus these vectors is bounded? The infinity norm is bounded. It's an impossibly beautiful conjecture about which we know very little. So Spencer's method gave a bound of the form log n. Banashik used a method from convex geometry to prove root log n. And Bansal, Dalish, and Garg gave a beautiful proof of the same bound using semi-definite programming. So an algorithmic but randomized bound. So this is really a wonderful conjecture. And just to know, it generalizes the Beck-Fiala conjecture, which perhaps for you is perhaps not such great motivation, but for people in combinatorics, that's people like Beck-Fiala a lot. Anyway, so I've run out of time, so thanks very much for your attention.
Thank you. Okay, I guess we can open the questions. Is there any question?
Yeah, I have one. It's about like these Odlisco simulations. What exactly is like? It was already aiming for some polynomials that would have, because you said that the annulus seemed to stabilize, right?
Yeah, I'm literally just looking at these two pictures. For me, like it seems like incredibly close together, right?
Yeah.
Nothing has changed the ratio.
What exactly was he plotting? Was he plotting like all polynomials or just these?
Sorry. So this is, so he searched through all polynomials, and so I'm not sure exactly what he was optimizing. I forget, but I think maybe it was the ratio of the maximum to the minimum. And then he just chose I think the actual best one.
Okay.
And then he noticed that a lot of the really good ones had some symmetry. Like if you looked at the first half and the second half, they were skew symmetric, I think he called them. Which I assume that means that this guy is minus that guy or something. Which is another actual motivation for us to think about these sine polynomials and cosine polynomials.
Okay.
Yeah, so I think this is the best. He said skew symmetric polynomial. This is the best skew symmetric one.
Okay.
Right.
And also about that when you kind of write a polynomial as a cosine polynomial and a sine polynomial, I think at the beginning you said like to just separate just a partition, but at the end the cosine ones would just be the small ones, so you have the
Right.
or is it random?
The cosine ones in the middle. So yeah, we can choose which ones are going to be. Yeah, so it's still a partition, but the cosine ones are just a subset of the guys of size at most. I don't know, roughly gamma, and then the rest sine. So most of it is sine.
All right. So my question is like, do you have to randomize over it, or you just like choose one and the argument works?
Right. So yeah. So we just so for the sine we can just do anything. Basically, so for the cosine, it just needs to be low degree. I mean, so in practice, what we do is these Rudin-Shapiro ones. So this is literally the polynomial that we take.
I see.
Right. So exactly this one. And then just all of the rest we can just deal with the sine.
I do have another question.
Yeah, please.
You guys thought about higher dimension?
Right. So yeah, what exactly would that mean?
Like you have
yes,
more ones.
Yeah. So right. So we can take a polynomial of complex numbers cross complex numbers or something.
Yeah.
And
So
then,
yeah, two variables, two complex variables.
Right. Yeah, so I should admit that at this point, this is sort of the extent of my analysis. So I'm not sure I can even visualize complex numbers plus complex numbers. Yeah, so I don't know of any questions in this direction, and I'm not really sure why. Whether suddenly things become obviously false or obviously true or something. It seems natural. And I guess these original questions were motivated by Fourier analysis. I don't know whether in high dimensions it has the same motivation or not.
Yeah, I don't know if there is a version Rudin Shapiro polynomial more variable. Okay.
Yeah, so I'm not even certain what the correct question would be.
Yeah.
I should admit that. So I'm not really an expert on this area at all. So literally we got together for a month in a place in Italy, and Julian suggested this problem because he basically thought that something combinatorial should work, and we spent a month trying to solve it, and on the last day of the month we solved it and then wrote it up and then never thought about it again. So I don't have yeah, I'm afraid the broader perspective is I'm not the right person to ask. Yeah, I can ask Julian and get back to you. He spent a lot more time thinking about these kind of questions than I have.
Yes.
Just a curious question. You have a polynomial whose spectrum is all integers from 1 to n or 0 to n. Yeah.
Okay.
I mean, you take
Yeah.
all the monomials from 1 to z to the n. So
Yeah.
I guess you can cook an arithmetic progression by changing z by z square or something like that. You can get a polynomial with all the even. And I wonder if you can get a spectrum inside a square-free integer, for instance. It's not exactly an arithmetic progression. It's not so far from an arithmetic progression, but
I'm not
it depends the set.
I understand the question.
Get a polynomial
Mhm.
with plus or minus 1 z to the n, and n is only a square-free integer. Whether it exists or not. I mean, the L2 norm is also square root n. I mean, 6 by pi square square root n. I mean,
So I think I'm not quite certain that I understand the. The theorem for everyone.
Instead of epsilon k z to the k, imagine a polynomial epsilon k z to the nk.
Okay.
Nk is a sequence of the square-free numbers. So
I see.
square-free integers from 1 to n. Yeah.
I see. Right. I do not see why that should not be possible with the same method. I mean, so for the sine polynomial, everything should be fine, I think, because you don't really care so much what the numbers are, but especially if they're quasi-random like that.
Yeah,
the cosine polynomial
it's initial construction, which is
the cosine polynomial construction. So right, so if you don't care about polylog factors, then you could just take the cosine polynomial to be random and everything should be fine.
Okay.
So yeah, so the missing step, as you say, should be replacing this with something that works, which doesn't sound. I mean, it sounds like the kind of thing that one could do with Spencer's method as well. Given that Spencer gave so many polynomials that work, probably you can prove that one exists, and then by multiplying it again by these z to these very fast oscillating things, you can get your things to be short and well separated. And then the lemma that we need is literally just if the intervals are short and well separated, then the sign things work.
Okay.
So there's some very specific properties that are sufficient, and they're quite simple properties. And anything that sort of rotates quickly should work. Like it doesn't. We don't need any properties of the Rudin-Shapiro polynomials except the fact that they're bounded from above. So I think to do what you want, you could just you could do this non-constructive Spencer argument, and then I think it would be fine. I think. Yeah, I don't see any problem.
Okay. Beautiful.
Yeah. The nice thing about doing things randomly is that things are generally quite flexible. So there's no structure to maintain. It's just,
okay. Thank you.
cool. Thanks.
Okay. So any other questions? Okay, so let's thank Rob again. And well, thank you for
Thanks very much. It was fun.
Yeah, thanks.